Hi, thank you all for coming. Ooh. Yes, okay. So my talk today will be indeed about perceptual learning and the potential role in supporting future value-based decisions. And I'm kind of new to the field of learning, but when I first started to get interested in formal reinforcement learning theories, I noticed that the comparison of value or the evaluation of outcomes once we have made a choice is often related to the dopaminergic changes, but also to the activity patterns of the prefrontal cortex and the striatum. But what I want to talk to you about today is actually the back of the mind. And I want to do that because I think that as primates, we are very heavily often relying on perceptual information. And this perceptual information is often very, very complex. And if you go into the literature and search for a relationship between learning and perception, you find some very interesting studies where they show value differentiations in early visual cortex, but also more recent work from Hikosaka's lab, actually finding visually responsive neurons in the tail of the caudate, which is a very important region in learning about action values and future action plans. But yet, I think we still know very little about the role or importance of perceptual learning in value-based decision-making. And I'm going to explore this question with you a little bit by reanalyzing a data set that I recently published, where we had a different focus, but where we had scanned 49 participants using Michael Frank's classic reinforcement learning task. Now, this task actually has two parts, a learning phase and a transfer phase. And in the learning phase, we basically presented participants with 3 pairs of faces, asking them to learn which face identity was the best one in each pair. And how they learned this is by actually seeing what kind of feedback they received after they had picked a face. And in this task, the difficulty or the uncertainty of learning is varied by reducing the reliability of feedback. Now, in the transfer phase, we asked participants to pick the best face in 12 novel combinations using the same faces, but we no longer gave them feedback. So they now only had to use what they had previously learned about these faces to make the best value-driven choice. And to get into the value-driven process, so how do we learn and how do we update? We used the Q-learning model with 2 learning parameters and the inverse temperature parameter, but we fitted it with a Bayesian within a Bayesian hierarchical structure. And we did this really to get the most reliable parameters per subject, which we then used to get individual trial-by-trial Q values about the option that they were going to choose and the option that they were not going to choose, or the difference between them, and the reward prediction errors. Now, the questions that I want to focus with you on today are actually twofold. The first one concerns the learning phase, where I want to know how the bold response in perceptual regions actually relates to the online tracking of value beliefs at the time that you have to make a choice, but also to the evaluation of choice outcomes once you have already made a choice. And then I'm going to focus on the transfer phase and actually ask what is the importance of perceptual regions if you rank them among the more traditional regions in the prediction of future value-driven choice. Now, just to quickly go over the behavior with you, just the modeling output, we saw that indeed the value differences at the end of learning were biggest for the AB pairs, and they become smaller for the CD and EF, showing that the most stable value differentiations are actually in the AB pair and reducing with the reduced reliability of the feedback. And this is how you see all 6 stimuli pair ranked. Now, when we got into the brain, we were actually interested in the bold response, and I'm going to show you a very, very busy graph. What I want you to know is that the top row, what I'm going to show you, is the bold response in striatal regions and in perceptual regions, separately plotted across time for the AB, CD, and EF pairs. And on the bottom row, I'm going to show you how this bold response for each type of trials is actually modulated by the value differences that participants had on a trial-by-trial basis. Now, what we see in the striatum is that the dorsal striatum, so the caudate and the putamen part of the striatum, are actually modulated by these value differences, but only for the AB trials. So only when these value representations are very, very stable or become very stable. Now, what is interesting is that you don't see it in the comments, which is more associated with the prediction of rewards in the future and less so with actions. But you do see it as well in perceptual regions. And this is something that I found very, very interesting the first time that I saw it. Because, again, you only see it for the AB pair, the most stable representations. So after you have made a choice, you can receive feedback. And we also wanted to know how these regions actually respond once they receive feedback. So what we did is we estimated the bold response at the time where they receive feedback, and we run a multiple regression using the signed reward prediction error, which has a value component to it, and an unsigned reward prediction error, which is mostly surprise. And they were competing for each other to see whether they modulated the bold response. And what you see is that all striatal regions, as is well known, respond very heavily or are modulated very heavily by the signed reward prediction error. And on top of that, the ventral striatum is also modulated by the unsigned reward prediction error. Well, what we saw in the perceptual regions is actually a very similar pattern, that also in perceptual regions you see this modulation by the signed reward prediction error. And just as something that stands out, look at the difference of how the unsigned reward prediction error modulates the FFA in their comments. Now, now to the future. How is this relevant, I thought? What should we do with this? So to actually answer this question, I used the random forest machine learning algorithm, and I'm going to show you a very busy graph again. It's complicated, but come talk to me at the poster if you want to know more. But very briefly, what I did is I took the trial-by-trial beta values in 9 regions, taking 9 regions which we had previously published with this data that were relevant in the test phase, took the trial-by-trial beta values from these regions for each subject. We added the sign. So was it that participant had to choose between 2 positive, 2 negative, or a positive or negative option? And then for each subject, together you get this large data matrix that you can combine. You shuffle the rows, you divide the data in a separate training set and a validation set. And how random forest actually works is that it takes the training set, it samples data from it, random rows, and it creates 2,000 different trees. And each tree is going to predict whether a participant is going to pick the optimal or the suboptimal option. And the majority vote is the one that the forest is eventually going for. Now, we use this to test in the validation set how participants would pick in the transfer phase. And when we looked at all participants, the outcome was 65% correct. So this algorithm could actually predict 65 out of 100 trials correctly. But when we went to the good learners, this already improved to 70%. So this is less data, less subjects, better predictions, which already showed to me that we are looking at a model that is doing something with participants, with what the participants learned in the learning phase. And this also was shown when we looked at the agreement of the trees. So you have 2,000 trees, and they all agree or not agree, or there's a proportion of them agreeing on whether choice is correct or incorrect. And what we saw is that the more these trees agreed on that the trial should be optimal, the bigger the value differences at the end of the learning phase. So what is the ranking of these regions? I know that this model is doing something with learning and can good predict behavior, but if you look at the ranking of the regions, you can see what the importance is of each region contributing to the prediction of the forest. And what we found there is that the dorsal striatum is on top, right? The putamen and the caudate, they were doing something with choice, something with feedback, and here they are in the test phase on top. After that comes the pre-SMA, which is a region that is traditionally associated with choice difficulty, which to me sounded very logical. But what was interesting that the follow-up was the FFA. The FFA was helping participants make a best value-driven choice, and it was ranking very nicely in between the ventral medial PFC and the accumbens. So the differences between them are not that big, but it's still on top of it. And this, to me, altogether, actually led to the hypothesis that the perceptual bold modulations that we found in learning, driven by value and reward prediction errors, might actually serve to support learned biases in future value-driven choices. And with that, I'd like to conclude this talk and thank Thomas Knape, who did all the deconvolution work. Should be a special thank, and Jan Theus. And thank you all for listening.
We have time for a question if anyone has one.
Okay, great. So we'll stick to the schedule. Thanks for the first speaker.